Okay, so we're trying to find the volume of this object, this sort of region enclosed by this cone, given by z is equal to r in the turquoise here, and this dome given by z is equal to square root of 8 minus r squared in this kind of mauve color. And I tried to make the colors match with this GeoGebra picture that we've got here, which is very nice. Even if you can't draw it, I'm not going to attempt to actually draw this thing. Even if you use graphing technology, an online applet or something, it's a really good idea to have a picture to look at when you're doing these things. To be able to visualize multivariable calculus is very visual. To be able to visualize the thing that you're doing, the object that you're trying to find the volume of, or whatever it is, so that you can sort of, first of all, motivate the integrals or whatever it is that you're doing. You get the math from the picture, and also to make sure that what you're doing syncs up with the picture, that you're actually getting the region or whatever, the volume that you're going for. And so first of all, it may not look like these equations actually give us a cone and a dome respectively. If you think about the r as a constant, and a lot of the time letters which are not x, y, or z actually represent constant values, so it could be interpreted that way. But in that case, this thing would give us a plane rather than a cone. So the first tip-off that we're going to be using, and we are going to be using polar coordinates here, the first tip-off is that we have this r, which, in order to give us a cone, has to represent the polar arm of that we use in polar coordinates. So just to review very quickly, in polar coordinates, we can represent, if the line straightens out properly, we can represent a point in the x, y plane, or in rectangular coordinates here, rather than by specifying the x and y coordinates. We can use the angle theta that the vector that we get by connecting that point to the origin makes with the x-axis, and we can also make this right triangle here, and look at the length of the vector, which is then the hypotenuse of this triangle. The adjacent side will be the x-coordinate, the opposite side will be the y-coordinate, and we get this polar representation. X is equal to r times cosine of theta, and y is equal to r times sine of theta, and that just comes from that triangle, solving for the x and the y. And this is the same r. This is the r that we're looking at here. That's that exact same r. Of course, because of the Pythagorean identity, the first Pythagorean identity, sine squared theta plus cos squared theta is equal to 1, we get r squared is equal to x squared plus y squared, or r is equal to the square root of x squared plus y squared. And this actually, we'll move it down here, this actually allows us to see that this is not a plane, but rather a cone, and that this other thing is a dome which intersects the cone. And we can see that by making the substitution for the r. And this is also going to allow us to find the intersection, to find the polar region over which we're integrating. We'll do that in a moment. But z being equal to r can actually be written as z is equal to square root of x squared plus y squared, which does give us a cone. And this z is equal to 8 minus r squared. We can rewrite this as z is equal to square root of 8 minus x squared minus y squared. And that shows us that this object here is actually a dome, if it'll let me write on here, a dome whose peak is at the points 0, 0, square root of 8. Because when the x is equal to 0 and the y is equal to 0, when we're at the origin in the xy plane, we get z is equal to square root of 8 minus x squared minus y squared. And so what we're trying to do is find the volume of this thing, this sort of ice cream cone thing that we get when we look at the intersection of this dome with this cone. So that's what we're going for. And the way that we do this is we're going to use double integrals in polar coordinates. The first thing that we need to do is find the intersection of the surfaces, and that's this. You can't see it if I draw there. That's this green circle on the top there, and we need to project this thing. We need to project this thing into the xy plane. That's the region over which we're going to be over which we're going to be integrating, and we're going to represent that as a polar rectangle. We're going to represent that region in polar coordinates, and then take the integral of the upper surface, which is the dome, minus the lower surface, which is the cone. And that's going to give us, we'll do a little different color here, that's going to give us the volume of this ice cream cone thing. So the first thing we need to do is find that intersection. We need to find that the intersection of these objects, and then project that into the xy plane. When we say project it into the xy plane, we of course just mean let the z coordinate be equal to 0. Figure out when z is equal to 0, what are x and y, and that will give us the circle in the xy plane directly underneath this thing. So we find that intersection circle up here, and each point in that circle has an x coordinate and y coordinate and a z coordinate. We let the z coordinate be equal to 0 and figure out what the x and y coordinates are, and that projects it onto the xy plane there. So that's the first thing we do, and that will give us the region over which we're integrating. So in order to do that, we're going to look at the Cartesian representations of these things. I think it's a bit easier to start that way, and then convert it back into polar coordinates. So we let these two things be equal. We let square root of x squared plus y squared be equal to the square root of 8 minus x squared minus y squared. And then we can square both sides and say this is true exactly when x squared plus y squared is equal to 8 minus x squared minus y squared. Now we can add x squared and plus y squared to both sides, add x squared and y squared to both sides, and we get 2x squared plus 2y squared is equal to 8, and then we divide both sides by 2 and get x squared plus y squared is equal to 4. And this is the circle of radius 2 in the xy plane. So this is telling us that, and what's the color that's going to stand out here? This is telling us that circle there in the xy plane has equation x squared plus y squared is equal to 4, or 2 squared. So that is the equation of a circle with a radius of 2 in the xy plane. So that is the polar region that we're going to be integrating over. And we'll review how we do polar integrals and how we chop this thing up. So let's start by drawing it down here. So it's always a good idea to draw sort of a two-dimensional picture of the polar region that we're integrating over, and then think about how it's being sliced up, how it's being partitioned, so that we can take the integral. So this is our circle with radius 2. This is -2, 0, 0, -2. That's our circle with radius 2 in the xy plane. And the way that we're going to think about this is, so when we take an integral, a double integral over a rectangle in Cartesian coordinates, so say we have a rectangle like, I don't know, here, say. This thing is bounded by, or it's determined by several intervals. So we have the interval from, say, a to b in the on the x-axis, and the interval from c to d on the y-axis. Let me extend that up a little bit more there. And so the idea is that I'm going to partition, let me do it in a different color, the interval from a to b, and get these partition points which chop this thing up like so. And I'll just draw in a few more to make it clear. And then I'm going to chop up on the left side the interval from C to D. I'm going to partition the interval from C to D, and that gives me these partition points, right? I cut it into these little pieces, and this gives me these little sort of cross-sectional, I'll try to get it a little bit straighter than that, squares which are going to be the sample points. And so I can call this partition pair here, this is, say, xi here, and this one is xi minus 1. And then let's call this point yj minus 1, and this one is yj. So this is the general y partition interval, which is of length yj minus yj minus 1, and this has a length of xi minus xi minus 1. And if we look at where these things meet, where they intersect, so let me try to actually get it in the right spot. It's up here. This is our partition square. And so we take our sample point, xi star, yj star here, and we evaluate the function that we're trying to integrate over at that point. So we look at f of this thing, and we integrate from where the x's are going from a to b, and then the y's are going from c to d, and then our infinitesimal unit of area is the delta x, or the when we take the limit, the dx, which is the length of that x interval, and then the delta y, and when we take the limit, the dy, is the length of the y interval. And when we multiply those two together, you get the infinitesimal unit of area. So the area of that actual little box is going to be delta y times delta x, or in this case it'll be xi minus 1 times yi minus y, or yj times yj minus 1. And when we take the limit, this is going to turn into delta, or dx dy. So I'm multiplying by this dx dy. This is the dA, the infinitesimal unit of area. And so what I'm thinking about, again, these are limits of Riemann sums, right? As the what we call the mesh of the x partition, the length of the largest interval goes to 0, and the same thing, the mesh of the y partition goes to 0. These are going to limit out to the actual volume of whatever function is lying above this rectangle in the xy plane. So we're sampling, we're making smaller and smaller partitions, picking sample points in each one, and then and then evaluating the function at those points. So seeing how high above those points the function lies, and that's the f of xi star y j star, and then multiplying it by this infinitesimal unit of area, this dA, which in this case is the dx dy. And if we're trying to find the volume of an area enclosed between two functions, f and g, then it would just be the same integral, but we'll be doing f minus g, where f is the upper one and g is the lower one. And so we're going to be doing that, except we're not doing this in rectangular coordinates. We're doing this in polar coordinates. So we have to do something a little bit different. And that's what we have this picture up here for. Let me actually just move all this stuff down and out of the way so we can see clearly what we're doing with the polar rectangle. And I'm calling it a polar rectangle because the same way that this is a rectangle determined by these points A, B, and C, D, so I take the x's in this interval from A to B, and the y's in between C and D, right? I get A is less than or equal to x, is less than or equal to B, and y is C is less than or equal to y, is less than or equal to d. This gives me a rectangle as a function of the x and y's, or determined by these x's and y's. This is an ordinary rectangle in Cartesian coordinates. What we're going to be looking at up here is actually what we call a polar rectangle. A polar rectangle. And this is determined, we saw that polar coordinates, instead of x and y, they use a theta and an r. So the length of the radius, or of the polar arm, in this case the radius of the circle, and then the angle that it makes. So we're thinking about looking at this arm going all the way around the circle and tracing out the region. And every point in the circle is determined by letting by taking some theta, right, moving this arm to some point theta, and then letting the length of the arm vary from 0 to 2, right? All the points in here are going to be on the tip of some ray, which is either, it goes from, when it's 0, that's the origin, and when it extends out up to 2 and stops, it gives you that entire line. And as I spin this ray around the circle, it traces out, or around 360 degrees or 2 pi radians, it traces out the entire circle. So I can actually write this rectangle as r of theta, capital R of theta and little r. I can say this is determined by r being in between 0 and 2, and then theta being in between 0 and 2 pi. If I let the theta range from 0 to 2 pi and the r range from 0 to 2, that gives me this entire circle. All of the points in the circle lie on some ray whose length is in between 0 and 2, and which has been rotated from the starting position at 0, or at 2, 0 here, 360 degrees or 2 pi radians around the circle. So that is the polar rectangle that we're going to be integrating over. And now I just have to think about how I'm going to partition it. The same way that I partitioned this rectangle here by chopping up the A to B interval on the x-axis, and then chopping up the C to D interval on the y-axis, I need to chop up these intervals, the r going from 0 to 2, and the theta going from 0 to 2 pi. I need to partition those and find these infinitesimal polar rectangles. So just like I had the dAs down here, which was the dx times dy, I need to find this infinitesimal unit of area in polar coordinates, so that I can multiply that by the function, evaluate it at the sample points, and integrate over the bounds. Where does the theta go from? Where does the r go from? And in the case that we're doing, I'm going to have to subtract the upper function from the lower function to find the volume of that intersection area, or region. So let me think about how to do that. Well, if I didn't want to erase that entire thing. This is a mess. Okay, hold on. Actually, let's just get rid of this and then put it back is probably the easiest way to go. So I think it was there. Yeah, that looks good. So the way that I'm going to think about this is I'm looking at, let's do it maybe in this color still. I'm looking at chopping up this interval, this theta interval from 0 to 2 pi. So suppose I'm going to go from theta sub I up, and then a little bit more to the next one to theta sub I plus 1. So I've got this little sliver of angle here. This is my delta theta. There is theta sub I, I did I plus 1 minus theta sub I. And that corresponds to being like the xi minus xi minus 1, just with the slightly different indices. Because it doesn't matter what the I is, if it's I plus 1 to I or I to I minus 1. As long as it's the next one up, as one is one more than the other one, we're solid. Then what about the r's? The r's are going from 0 to 2, and at each point I can stop. So like here, this is say r j, and then I go up a little bit more to r j plus 1, and this distance, which I'll try to do in maybe like a highlighter color, this distance, that's not coming up, this distance there, right, that is the delta r, which is r j plus 1 minus rj. And so the same, and that corresponds to like the delta y being the yj minus 1. And so the same way that that delta x and that delta y gave us this infinitesimal unit of area, dA, where we're going to take the sample points, which was dx dy, this is going to give us this polar rectangle, this infinitesimal polar rectangle, which is this orange thing here. And I really want to sort of highlight the shape of this because, there we go. This thing is curved, right? We can see on the top that it's curved. It's not a normal rectangle. And I'm going to actually highlight this in a darker color just to really, really emphasize that. There we go. It's this kind of, because we're rotating around the circle, it's this curved shape, right? It's determined by this angle theta. So it's this thing, if we pull it out, it looks like kind of that. It has this curve to it. So it's not just a delta theta times delta r, the same way that the rectangle down here, which if we cut it out looks just like that, right? This was delta x times, or I'm already switching to limits, that doesn't come yet. This was delta x times delta y. This thing isn't quite so simple. I have to think about actually what is the area of this thing. And so the way that I do that is I look at if I cut out the entire sort of sector of a circle, right? Because I want to find out what is this length, what is this this curved thing here. I know that this is delta r, right? That's straight up and down. I went from delta r to delta r or from r sub j to r sub j plus 1. That's delta r. But what about this thing? Well, in order to figure that out, I need to think about what is the arc length of a sector of a circle cut out by some angle theta. I'm interested in this length here, this thing there, this arc length cut out by this angle theta, because that corresponds to this piece that I'm cutting out there. And this also, of course, depends on the r, but I have this one corresponds to this r sub I, and this one, that's that, and then this one corresponds to like the r sub j plus 1, a little higher one. Their lengths, those little arc lengths, these sides here, are going to be determined by the angle and the radius, how far we went out. You can think of them as the arc lengths at the edge of a circle with a radius of r sub j or r sub j plus 1. So we need to find out what is in order to determine this infinitesimal quantity of area, what is that arc length? Well, I know that arc length, that piece here, right, cut out by this angle theta of a circle with radius r, I know that the ratio of that to the total circumference of the circle, the entire arc length of the whole circle, which is a sub theta over what's the circumference of a circle with a radius of r, it's 2 pi r. I know that has to be proportional to the amount of angle that cut out this arc, this sector of the circle. How much angle was that? That was theta. And how much angle is there in the entire circle? There are 2 pi radians. So this just expresses this relationship, this key relationship between the arc length of this sector of the circle to the entire circumference of the circle and the amount of angle that determined it. So and you can see that when theta is 2 pi, right, the right side will be 1, and the a sub theta will be 2 pi r, the entire circumference of the circle. So I can use this relationship to solve for a sub theta, the arc length of this sector of the circle. This is 2 pi r times theta over 2 pi. And then, of course, the 2 pi's cancel, and it ends up just being r times theta. So this thing here, this is actually this arc length there, that is ri times, in this case, it is the delta theta, right? Because how much angle is this? This is theta sub I plus 1 minus theta sub I, which is delta theta, and this should have been in r sub j. And this one, because we're using j's for the r's and i's for the thetas, this one up here, determined by that next r up, the slightly longer r, which is r sub j plus 1, this is going to be r sub j plus 1 times delta theta. And so we get, the point is that we get this factor of r in here, right? This side of the thing is delta r. Let me do this in maybe orange. This is delta r, this side there, and then the other side of the thing is going to be delta theta times either r sub j or r sub j plus 1. When we take the limit, right? When we take the limit and we get the delta r turning into a dr and the delta theta turning into a d theta, we can just, instead of looking at the difference between these r sub j's and r sub j plus 1s, we can just say this is r, right? As we take the limit, those things get closer and closer together. The r sub j's converge to the r sub j plus 1s. That's the whole point of taking these finer and finer partitions, is that the distance between the r sub j's and the r sub j plus 1s and the delta i's and the delta I plus 1s goes to 0, the same way that the difference between the xi and the xi minus 1 went to 0, the yj and the yj minus 1 went to 0. So we can just say, because they're basically the same, or they limit out to the same number, the distance between them goes to 0. I want to be very careful about the way I say this. It's kind of hand wavy saying they're basically the same. The distance, the difference between them goes to 0 as we take these finer partitions, as the mesh of the partition goes to 0. And so we get, and this is the whole point of this, we get our dA, our infinitesimal unit of area, is r times dr times d theta. So that was the moral of the story of this whole thing that we're doing here, is we were trying to find what is the corollary, the polar coordinates corollary of this infinitesimal unit of area dA, which was, in the case of rectangular coordinates, dx dy. In the case of polar coordinates, it is r dr d theta. So it's not, people always want to say that it's just dr d theta, because the r is varying and the theta is varying. We take the limit from the delta r delta theta, but we actually need this extra factor of r in here. That's very important. That's the thing that people always forget. So the way that we find the area of or the volume of a solid over a polar region is if our theta, say our theta is in between alpha and beta, and then our r is in between gamma and delta, we're going to take the integral with the r ranging from gamma to delta and the theta ranging from alpha to beta of f of, now instead of the x star and the y, or the xi star and the y sub j star, this is going to be r I star cos theta j star, and then ri star sine theta j star, because our xy point is actually r cos theta, r sine theta in polar coordinates. So we express the point as r sine theta, r cos theta, and then we multiply by r dr d theta. And of course, when we take the limit, we can forget these star things. And let me just bring this down here, and we get, and this is the final form that we're going to be using. I'll just rewrite it. It is integral with r going from gamma to delta and theta going from alpha to beta of f of r cosine of theta, r sine of theta times r dr d theta. This is it. This is the polar integral. And we have to keep in mind, of course, that the r bounds here, the gamma and delta, are on the inside, and so is the dr. And then the theta bounds, the alpha and beta, are on the outside, and so is the d theta. Same way that down here, the dy had the outer bounds, and so the dy was outside of the dx. The dx was in here, and the inner bounds are the x bounds, a and b. So that is how we do a general polar coordinates double integral to find, and that would find us the volume of the area from the xy plane, which we're looking at here, up to whatever that function f is. We have some function defined on this polar rectangle, this circle, so it gives you this surface over top of it, and then there's some volume trapped in between that surface and this polar rectangle. And this will give you the volume of that. If we have two surfaces, which are on top of this polar rectangle, and there's some area trapped, or some region, some volume trapped between them, the volume of that region is going to be given by integrating the difference of those functions over this region. So we subtract the upper function from the lower function and compute the integral the same way. And so that finally brings us back all the way to this thing here, which is our function that we're trying to integrate. The cone, the z is equal to r, is the lower function, and then the dome, the z is equal to root 8 minus r squared, is the upper function. Right? We're trapping that area, that volume, which we looked at here. We're trapping this. Actually, let me do it in even more obnoxious color. We're trapping that stuff in here. The dome is the upper function, the cone is the lower function. So we're going to be subtracting the equation for the cone, the z is equal to r, from the equation for the actually I need to move it even farther down, for the dome, over this region. And we already decided that region, that x squared plus y squared is equal to 2 squared, the circle with radius 2 at the origin. That can be expressed as the polar rectangle r of theta and little r, where theta is in between 0 and 2 pi, and r is in between 0 and 2. So these are the bounds that we're going to be using, and then our functions, z is equal to r, and z is equal to square root of 8 minus r squared. Those are the upper and lower functions, respectively. So actually, I don't need to move those down again. So let's set up our integral. We are going to be integrating the r's are going to be going from 0 to 2, and the thetas are going to be going from 0 to 2 pi. And what is the upper function? It is z is equal to, in polar coordinates, it's 8 minus r squared. And in we could, by the way, rewrite this in Cartesian coordinates, but then we'd get the squaring and the r pulling out and canceling, and it would go back to that normal form, right? You can try that. You can put in x squared plus y squared for r, and you'll see that we get the same thing. But we already have it written in polar coordinates, so we're just going to keep it the way that it is, and just do it down here. And we're going to have, this is again our f of r cos theta, r sine theta. I'm just mentioning that because we might be looking for an r and a cos theta, an r and a sine theta, and you might be saying, okay, well, where did the cos theta and the sine theta go? The idea is that when you square the r, so if you put in x is equal to r cos theta and y is equal to r sine theta into this equation, and you would square them, and then the r would factor out. You get a factor of r squared, and then the sine squared and cos squared would become a 1, and you'd get this same equation. So just in case that looks weird, I wanted to mention that. But if you're okay with that, that's terrific. Because we would have minus g of r cos theta, r sine theta, and then we throw in our r dr d theta, and of course our f is square root of 8 minus r squared, and our y is just r. This is z is equal to this, or f of r and theta is equal to this. This is z is equal to r. So we get this thing being equal to, and I'll just duplicate it and bring it down. This thing is equal to the integral with r going from 0 to 2 and theta going from 0 to 2 pi of square root of 8 minus r squared minus r upper minus lower times r dr d theta. So this is the integral that we need to do. We need to evaluate this thing first with respect to r. We'll see how to actually do this. First with respect to r, the r bounds, and when we integrate and evaluate that, substituting in those values of 2 and 0 for r, we'll get rid of the r's. We get something which doesn't involve any r's, and then we integrate that thing with respect to theta. Substitute in the 0 and 2 pi for the theta, and that gives us just a number. So let's see if we can do that without screwing it up too much. And so the way to do these is working from the inside out. I'm going to first think about this integral from 0 to 2 of square root of 8 minus r squared minus r times r dr, and I'm going to evaluate that and then plug it back in, whatever I get from that, and evaluate that, take that as an integral with respect to theta, with a definite integral with bounds of 0 and 2 pi. And so, but the first thing I need to do is this. So I distribute in the r's to begin with, and I get the integral from 0 to 2 of r times 8 minus r squared dr. And I can conveniently split this up into two integrals. I can make this integral from 0 to 2 of r times root 8 minus r squared minus, I should put in the dr as well, r squared dr, minus integral from 0 to 2 of r squared dr. Now this one is, of course, just r cubed over 3, evaluated from 0 to 2, which is, of course, 8 over 3. So I have to remember, after I do this other one, I'm going to subtract 8 over 3 from it. But the one that actually involves some work is this thing, integral from 0 to 2 of r times root 8 minus r squared. So I want to first find an antiderivative for r times root 8 minus r squared dr. I'm, of course, going to do this with a u substitution. I'm going to say u is equal to 8 minus r squared. This gives me du is equal to negative 2 r dr. And that was the whole point, is that I'm just off by a factor of negative 2 here. I have the dr and the r, and I'm missing a negative 2. So I can say that this is equal to negative 1 over 2 times the integral of the square root of u du, which, of course, I put this in exponential form. This is integral of 1 over 2 integral of u to the 1 over 2 du, which is negative 1 over 2 times, what is this antiderivative? This is u to the 3 over 2 times 2 over 3, so that the constants will cancel. Maybe I'll put it over here, and this is less disorienting. Right, I need the 3 over 2, and I take the derivative to come down and cancel with the 2 over 3, and I subtract 1 from it, and I'm left with the 1 over 2. And of course, the 2's cancel here, and so I'm left with negative 1 over 3 u to the 3 over 2, but I had my substitution, u is equal to 8 minus r squared, so this ends up being negative 1 over 3 times 8 minus r squared to the power of 3 over 2. Is my antiderivative. It was not an indefinite integral, though. It was a definite integral with bounds from 0 to 2. So I now need to evaluate this thing from 0 to 2. Actually, I don't need to unsubstitute. I could have evaluated u going from, so u of 0 is 8 and u of 2 is 4, so I could have been saying u going from 8 to 4, but it doesn't matter. I can unsubstitute and use the normal r bounds. That's totally fine. I get the integral of negative 1 over 3, 8 minus r squared to the 3 over 2, going from 0 to 2. R is ranging from 0 to 2. This is, of course, negative 1 over 3 of 8 minus r squared, so 2 squared, which is 4, to the power of 3 over 2. And then I'm subtracting negative 1 over 3, 8 minus 0 squared, to the 3 over 2. this is negative 1 over 3 times 4 to the power of 3 over 2, and plus, this is going to be, because the negatives will cancel, the negative and the negative 1 over 3, 8 to the power of 3 over 2. 4 to the power of 3 over 2 is 8, because square root of 4, the 4 to the 1 over 2 is 2, cubed is 8, so I get negative 8 over 3, plus now I have to evaluate 8 to the 3 over 2, and so the square root of 8 is 2 times the square root of 2, and then I cube that, so we can actually I don't think there's a nice way to write this. I can write this as, let's just say, you know what, I don't think it's even going to simplify it. We'll just say this is square root of 8 cubed. And then, because we're just looking for a number here, so it doesn't matter, you can clean it up if you like. But this is this part of the integral. This is where'd it go? This thing here, and then the other thing is 8 over 3. So we have to subtract this part, which was 8 over 3. So we're subtracting 8 over 3, and I'm going to end up with 8 to the power of 3 over 2. I guess we'll leave it in exponential form. Minus 2 times 8 over 3, so minus 16 over 3. That is my integral. That is my integral with respect to r. So that was this interior part of the thing. That was this bit. And now I have to integrate whatever I get out of that from 0 to 2 pi with respect to theta. So I now get to say I'm looking for the integral from 0 to 2 pi of 8 to the 3 over 2 minus 16 over 3 d theta. This is, of course, 8 to the 3 over 2 minus 16 over 3 times theta, with theta going from 0 to 2 pi, which is just going to be 2 pi times 8 to the power of 3 over 2 minus 16 over 3, which is not pretty, but it's a number, and that will be the volume. So assuming I didn't make some silly mistake anywhere, that is our answer. Of course, it's never a bad idea to do these things yourself and check, because who knows what's going on in here. But the important thing is the process. The important thing way back up here is this, right? The double integral in polar coordinates for the difference between the two functions. The all the way back up here, upper minus lower thing. And in general, the important thing here is understanding how we get these polar rectangles, why we need this r times dr d theta as the infinitesimal unit of area, and why we have this thing. This is the big deal. This integral, this polar integral over a polar rectangle determined by these bounds for r and theta, and then it's just a matter of finding out what the f is, and if you're trying to find the volume of a region enclosed between two surfaces, just figuring out which is the upper surface and which is the lower surface, subtracting them, and then being very, very careful with the integral, because it's really easy to make little mistakes and screw up the whole thing.